Hi there. This is intended to be a review of super basic matrix and vector notation and tools for those of us who may forget our basic matrix algebra. So a vector is just a bunch of numbers arranged in a column or in a row. Usually they're given a hat, so this is my vector. This is a row vector. This one's a column vector, right? And the number of elements in your vector determines its dimensionality. So the x and y coordinates that you're used to seeing in Cartesian coordinates, you can think of those as being vectors, right? X and y is a vector with an x coordinate and a y coordinate. It can help to think of vectors as being rows or columns in a spreadsheet, say. We're the Excel generation after all. A matrix is just a bunch of numbers arranged in a rectangular grid, sometimes a multidimensional grid, but we'll just go with the two-dimensional matrix, usually denoted by a capital letter. So A is, there's my matrix. It's got two rows, it's got two columns. We always say that a matrix has m rows and n columns. We talk about m by n matrices quite often. My brain thinks of matrices as being stacks of row vectors. Some people might think of them as being smushed together column vectors. Whatever works for you. And a matrix that has the same number of rows and columns is called a square matrix for obvious reasons. And square matrices have a lot of special properties, and you'll see quite a lot of them as we go on. For both vectors and matrices, you might want to have a way to refer to the elements that are inside them. Usually for matrices, you use whatever letter the matrix, the capital letter the matrix is named for, and use the lowercase version of that, and then give it subscripts to say which element in the matrix you mean. So A11 is in the first row, first column, and that's this one. Rows count from the top down. Columns usually count from left to right. So A11 here is going to be equal to 1. The 1/2th element is row 1, column 2 is 2, and so forth. With vectors, same kind of thing, or similar thing. You could also, let's reverse a second. You could also say A11, the first row, first column element of A is 1. And with vectors, same sort of thing. You say the first element of the vector V is 1. Or maybe V subscript 1 is 1. Right. Referring to this one here. So two other important kinds of matrices are identity matrices and transpose matrices. The identity matrix is denoted by I, and it's just a matrix that has ones in the diagonals and zeros everywhere else. So that's the identity matrix of dimension 3 by 3. Every number has its own square identity matrix that's of that dimension. A matrix transpose, so for any matrix, capital A, so I'm going to define a matrix A. It's going to have two rows and three columns, so that's a m by n 2 by 3 matrix. If I transpose that matrix, transposing a matrix basically means rotating it, flipping its rows for columns. So the transpose of my 2 by 3 matrix is going to be one with 3 columns, or 3 rows and 2 columns. So it means that the 1-2 element is going to become the 2-1 element. You're switching your two dimensions. And that'll be the same for everything. So A transpose is going to be 2, 4, 1, 5, 3, 6. So I just flipped it. I think of it as being flipped sort of 45 degrees, but I guess it's actually 90 degrees really. So the transpose of a matrix takes its row and each one of its row and column elements and flips its rows for columns and puts them in the other space. So in general, that means all A element ij become a transpose element ji. Vector and matrix addition is pretty straightforward. You can only do addition if you have two vectors that are the same size. So if I've got some vector u and another vector v, then u plus v is going to be the first element of each one, 1 plus 3, and then the second element's added together, 2 plus 4 is equal to 4 and 6. So you're just adding the elements together in order. And if I have two matrices, simple 2 by 2 matrices, right, A and B, then A plus B is just going to be the same size, and this is going to be A11 plus B11, 2 plus 1. And this is going to be A12 plus B12, 0 plus 2. This will be 3 plus 1, or 1 plus 3, whatever. And this will be 3 plus 4. Just adding up the elements that go in each space. 3, 2, 4, 7. Right? And note, because you're adding up the elements that have the same row column index, if A and B are different sizes, have different numbers of rows and columns, you can't add them together. And if your vectors have different numbers of elements, you can't add them together or subtract them. And this works fundamentally the same way with subtraction. There are actually lots of different ways you can multiply vectors and matrices together, different kinds of products. I'm just going to focus on what you're used to thinking of as multiplication, sometimes called dot product for vectors and matrices, which is, and there's some funky, let's skip that. So let's say I've got two vectors again. U is, I don't know, a row vector, and V is a column vector. So because of the properties of vector multiplication, I can multiply U times V which is going to be which is a lot like addition, the first element of each vector multiplied together. So it's going to be 2 times 1, 2 times 1, plus the middle ones, 1 times 2, plus the end ones, 3 times 3. Which is 13. So what I actually did there was U1 times V1 plus U2 times V2 plus U3 plus V3. And you can do this as long as they have the same number of elements. But there's also a funky rule about row vectors and column vectors. You can try this in MATLAB, and it will agree with me. You cannot multiply a row vector by a row vector, and you cannot multiply a column vector by a column vector. You can multiply a row vector times a column vector if they have the same number of elements. But you can't multiply, so in this case, u is a row vector and v is a column vector, so I can do this multiplication. But if I tried to say, what's v times u? Well, v is a column vector and u is a row vector, so if you try and do that, it won't let you. So it matters who is on the left when you talk about row and column vectors and vector multiplication. And there are other ways to multiply vectors together. The scalar or cross product comes up every so often in geometric dealings, but I haven't had to deal with it in population stuff, so I'm going to skip it. But there should be an external resource if you want to review cross products and some other products. So if I want to multiply a vector and a matrix together, there's even more rules about who can have how many rows and columns, and who can be on the left. Let's say I've got a matrix, and I'm just going to give it variables in it, call it A, B, C, and D are its elements, and a vector, it's got X and Y in it. So because A is square, I can multiply it by V. So if I want to multiply A times this vector, make sure A is on the left. The way I was taught to do this in high school is kind of visual, so I was taught to stick the matrix down here, A, B, C, D, and a vector above, X, Y. And then it's kind of a visual as to what you're doing. So you're actually doing a dot product of each row with its column vector separately. So the first element of my result is going to be A times X plus B times Y. And on the second row, we're going to get A times X times C plus D times Y. Another really easy way to do matrix multiplication is to define your matrix and your vector in MATLAB and just say some other vector is equal to A times V, and MATLAB will do it for you. And I'm going to define another matrix B. It's the same size as A. Let's give it X, Y, Z, and W. If I want to multiply A times B, it's exactly the same thing. I'd stick A here, B here. The result is going to be the same size. Have the same number of elements, I should say. And so for the first one, you get the dot product of this row and this column, which is AX plus BZ. And then this next element is the dot product of the second column times the first row, which is going to be AY plus BW. This element will be the first column and the second row, so CX plus DZ. And then finally this element is going to be this column vector and this row vector, CY plus DW. Because these are the same size, I could also multiply this B times A, which is going to be a slightly different thing. I'd say do this quickly for yourself, and you can prove to yourself that B times A is not necessarily the same result as A times B. Right? In terms of actual laws and rules of matrix and vector multiplication, the number one is that A times B is not necessarily the same as B times A. Remember, these capital letters all mean they're matrices. Right, but A plus B is always going to be the same as B plus A. And most of the other forms of addition work the way you expect them to. So A times the sum of two other matrices will be the same as A times B plus A times C. If you multiply a matrix product by some constant, it is going to be the same as multiplying each matrix by that constant. So if you take your sum of two matrices and you multiply that by a constant, it is going to be the same as multiplying them by constants separately. And in order for matrix multiplication to work, if A has m rows and n columns, B must have n rows and m columns. You can play around with trying to multiply matrices together and prove to yourself that that is so. Or you can try and get MATLAB to multiply matrices together, and it'll beep and give you errors if you try and multiply things together that don't have the right dimensions. And a final note about notation. Sometimes you'll see vectors written with lots of i's and j's and k's in them. So if you've got a vector that's of the form, say, ai plus bj plus ck. The I and the j and the k are all also vectors. They're called unit vectors. I is typically 1, 0, 0 column vector. J is 0, 1, 0 column vector. And k is 0, 0, 0, 0, 0, 1 column vector. And they refer to the three dimensions of our usual three-dimensional x, y, z coordinate space. So a times I just means you're going a steps in the I direction, in the x direction. It's similar. So I is typically what we think of as the x direction, j is in the y direction, and k is in the z direction. It comes up a lot in physics, just so if you see this notation with i's and j's and k's, they're unit vectors and they tell you what direction, they imply directionality in xyz coordinate space. So why are we relearning matrices and vectors and making sure we understand what they're doing? Huge parts of population biology depend on matrix algebra for their machinery, in part because of game theoretic models require matrices, the whole machinery of Markov chains, that comes later. But the primary motivator for me in my work is age and stage structured population models, because most of the things that we care about have age or stage structured life histories that affect how we need to model how those populations will change in time. So if I'm dealing with an age-structured population, my population number n becomes a vector. So the number of individuals of age 1, the number of individuals age 2, the number of individuals age 3, up into, whatever the final age is. And if I want to make projections about how my population is going to change in time, I have to be doing operations on this vector of populations at each age, which is why we end up doing matrix and vector multiplication. For example, the ever so famous Leslie matrix is a very handy way to do this. So for my example, an L matrix for an organism that has a 3-year life history, it lives a really short time. Classic one looks like this. Let's just do. So in the top row of a Leslie matrix, we put fertilities. And in this off diagonal, section, we put survival rates or transition rates. So in this Leslie matrix, this would be the fertility of 1-year-olds, but I'm assuming that newborns do not reproduce, so they have a fertility of 0. This S1 is the survival of newborns to become 2 years old, so survival from 1 to age 2. This S2 is the probability of survival from age 2 to age 3. Individuals that are age 3 die, so they have a 0. And this is fertility for individuals age 2 and fertility for individuals age 3. So at my initial time, say n is equal to n1, n2, and n3, individuals aged 1, 2, or 3. If I want to know how many the individuals there will be in each of these age brackets in the following year, I just multiply this vector by this matrix, which is n at time t plus 1 is going to be equal to L times n at times t. It's familiar looking, right? And you can kind of convince yourself without doing matrix multiplication that the number of individuals aged 1 is going to be the number of individuals of age 2 times their fertility plus the number of individuals at age 3 times their fertility, right? That's how many newborns there will be. The number of individuals age 2 in the next generation is just going to be the number of individuals age 1 times their survival probability. And the number of individuals age 3 in the next generation should be the number of individuals age 2 now times their survival probability. And you'll find if you do the matrix multiplication and multiply the matrix L times the vector n, these are exactly the expressions that come out of that multiplication. So there's going to be a lot more of this matrix model framework later on, but I just wanted to point out that there is a significant chunk of all of population biology that depends on this matrix machinery. So get it straight in your head if it isn't already. Before I go, I want to remind you of a couple of properties or features of square matrices, which are determinants and inverses. So I'm going to define myself a matrix A, 2 by 2 matrix. So the determinant of A is usually written as handily det A. And the determinant is a way to turn your matrix into a scalar that ends up being surprisingly useful in some fancy linear algebra stuff I'm not going to talk about right now. But you should at least remember that a determinant is a thing that exists. For this matrix, because it's a 2 by 2 matrix, it's a pretty easy thing to remember the value of the determinant is A times D minus B times C. So it's closely related to the cross product of vectors. Get that cross in there if you go A times D, C times B. For a 3 times 3 matrix, a very similar kind of combination of cross multiplying gets you the determinant of a 3 by 3. For anything bigger than a 3 by 3, it's a huge pain to calculate. So the easiest thing to do is to just define some scalar and ask MATLAB to calculate det bracket A, and it'll return the determinant of your matrix for you. Kind of similarly, the inverse of my matrix A, it's usually denoted as A prime, is defined by the fact that if you multiply a matrix times its inverse, so A times its inverse, you get the identity matrix, which in the case of a 2 by 2 is going to be 1, 1. There, like that. So given that you know what the end result of your matrix multiplication is going to be, and you know one of the matrices, you should be able to arrive at what the values in the other matrix are going to be. There are plenty of rules for doing that, but again, I'd suggest making a dummy variable and then asking MATLAB what the inverse of A is. These are just MATLAB commands. Because if you know what a determinant and an inverse is and what they're for, it doesn't really matter if you can do the simple algebra of actually calculating them yourself. That's just my personal opinion. And if you're thinking, why do I care about determinants and inverses? Well, as I was saying, if you have some expression AX is equal to B, where A is a matrix, X is a vector, and B is a vector, and you know what A is and you know what B is, kind of like up here, you know what A is and you know what B is. You can figure out what X is because by virtue of the way multiplication works, I can multiply both sides of this by the inverse of A, and have the equality remain, which means the identity matrix times X is A inverse times B. And since multiplying anything by the identity matrix doesn't change its value, that means you can find your unknown vector X by multiplying B times the inverse of A. So if you can find an inverse for A, it can make solving these sorts of linear systems much easier. And just as a hint, sometimes finding inverses, if you don't have MATLAB, involves determinants. So determinants and inverses are both pretty helpful for grinding out the algebra of finding the answers for things that MATLAB will just tell you.